In this video, I want to talk about Kirchhoff's current and voltage laws. So, in previous videos, you learn how we have defined the Ohm's law, which shows the relationship between the voltage across a resistor and the current that goes through it. So now let's just assume we have a circuit that is a bit more complex. So it has at least like a few resistors connected to each other. So a circuit is called to be solved if the voltage across and also the current in every element have been determined. So let's just say we have this sample circuit, right? I just put an independent current source. Let's just say I have resistor 1 here, this one I call it I1, resistor 2 here, and I want to make this very complex, right? So even though there is no reason for you to worry, because we will get to how we can solve such a circuit. And let's just say we have one extra resistor, call it R6 here, right? So for this circuit, we have this current source that basically feeds current to the rest of the circuit, but we have 1, 2, 3, 4, 5, 6 resistors, and for each one of them we don't know what is the voltage across them and what is the current that goes through them. Also for the current source, even though we know the current of the current source, but we don't know the voltage across it. If you remember from before, we said that for the current sources, they are designed in such a way to maintain a fixed current, right? No matter what is the voltage across the two terminals of the current source. So we cannot know what is the voltage across this current source until we solve the whole circuit. So a circuit again is said to be solved if the voltage across and the current in every element has been determined. So if it was a very simple circuit, if we only had, let's say, a voltage source and a resistor, something like this. For this one, since we had a voltage across this and we could find out a current that goes through the circuit through the Ohm's law, we were able to find out what is the voltage across the resistor, right? Or what is the current through the circuit. Because you see, it is a very basic circuit. We only have one source and one resistor. But when you have more and more complex circuits, Ohm's law is not going to be enough. You still use Ohm's law, but Ohm's law by itself is not enough. So let's just take a look at one example here. So here we have an example of a circuit that contains one independent voltage source. I showed it with this circle with polarity positive and negative like this. It is called Vs, and we assume that we know its value. Then we have 1, 2, 3 resistors, R1, RC, and RL. So the naming is from ourselves. You can name it whatever you want. So these are connected like this to this voltage source. And as you can see, for each one of them, we can define the two terminals, right? So for example, for this voltage source, we have one of the terminals here at point A, and the other one is at point D. For RL, the two terminals are D and C. And for RC, the two terminals are B and C. One other thing that we did these blue writings is that we have specified some indicative reference polarities and directions for each one of these elements. And we did this randomly, right? So at this point you can define or decide on any voltage direction or voltage polarity or current direction without any effect on the final result. So for example here I assume the positive polarity to be on the right side and the negative polarity to be on the left side. Based on this, I consider the current to go in the direction of the voltage drop. I decided on the polarity for voltage across RC as well, and also for the current. And the same for the resistor RL2. As you can see, since the resistors, we know that they usually consume power, I put their reference direction for the current in the direction of the voltage drop. So the power that we calculate for them is going to be positive. For the voltage source, since our understanding is that this voltage source is providing power, I put the reference direction for the current to be in the reverse direction of the voltage drop, or in the direction of the voltage increase. But we will get to more details later on. So this is based on the assignments that we had for the voltage polarities and current directions. So now, based on this, since we have the voltage source, so we know the value for the voltage source, so how many volts is that? Also, we know the values for the resistors, so we know the value for R1, how many ohms is that? The same for RC and the same for RL. But what are the unknowns in this circuit now? We said that if a circuit is solved, the voltage across and the current in every element should be known. So here, for the voltage source, even though we know the voltage across it, but we don't know the current that goes through it. For resistor R1, we don't know the voltage, and also we don't know its current. The same is true for RC and RL. So now, based on these, how many unknowns do we have? We have one unknown here, two here, two here, and two here. So in total, we have 7 unknowns for this circuit. So if we know all these 7 unknowns, we can say that this circuit is fully solved. As you can see here, I use terminal dots A, B, C, D to show the start and end points of individual circuit elements. So the points, these dots in which we have 2 or more elements connected, we call them nodes. So a node is a point where 2 or more circuit elements meet. And here I labeled these 4 nodes that we have in the circuit as A, B, C, and D. So given these circuits and these assignments that we did, we have to come up with values for 7 unknowns based on the known values that we have. We know the Vs, we know R1, we know RC, and we know RL. So from linear algebra, you know that if we want to find n unknown quantities, you must solve n simultaneous independent equations. So this is something that I would assume that you have learned in previous math courses. I will provide some reading material that you can go over it and refresh your memory. But the assumption here is that you already know this. So since we have 7 unknowns here in this circuit, we must find 7 simultaneous independent equations. So that is and important adjective. So these equations must be independent. Otherwise, we are not able to solve this circuit. So let's just go and find these 7 equations. So since we have 3 resistors, right, and for these 3 resistors we can use Ohm law to represent the relationship between their voltage and their current, we can easily come up with 3 equations. So these 3 equations each is the Ohm law that shows the relationship between the voltage for that resistor and the current that goes through it. So we have V1, the voltage across R1, to be equal I1 multiplied by R1. We have VC to be equal IC multiplied by RC. And finally we have VL to be equal IL multiplied by RL. So out of the 7 equations that we require, 3 of them can be easily found using Ohm's laws that show the relationship between the voltage across and the current that goes through each one of these resistors. But what about the last 4 equations? How can we come up with those equations? So as you can see, these Ohm's laws, they work based on the individual elements and they don't consider the interconnection between the elements. So the answer to finding those extra 4 equations that we need is to consider the interconnection of the circuit elements, because those interconnections kind of imposes some additional constraint on the relationship between the terminal voltages and currents. So these additional constraints or these additional laws are referred to as Kirchhoff's laws. So let's just go through them one by one. The first one that I want to discuss is the Kirchhoff's current law, which states that the algebraic sum of all the currents at any node in a circuit equals 0. So if you remember from before, I said that in this circuit I call the interconnection of all these elements, basically any point that 2 elements meet, I call them a node. So I have node A, node B, node C, and node D. So the Kirchhoff's current law states that the algebraic sum of all the currents at any given node in a circuit equals 0. So what does it mean? It means that if let's say I assume that I have a current called IM here. Also, let's just assume I have a current coming in this direction called IN. If I sum the values of these 2 currents, considering their direction at this node, the result must be 0. So in another word, the nodes do not provide any current to our circuit, or they are not drains to basically absorb any current, right? So any current that enters a node should basically exit the node as well. So to come up with this equation, what we need to do is that we need to come up with some reference directions. Basically, we should assign some positive or negative signs depending on the direction of the current. So to use this law, we use an algebraic sign corresponding to a reference direction that we assign to every current at any node. So the convention that I'm going to use here is that in a node, if we consider the leaving current to have a positive sign, the incoming current must be considered negative, and vice versa. So let's just take a look at what we have at node D. So at node D, as you can see, we have IS going from the left direction. Also, we have IL going toward the right direction. So at this node, we have IS basically coming to the node, and IL is basically leaving to the node. So now, should I consider the sign of the current that enters the node to be positive or negative? The answer to that is it doesn't matter. If you consider this to be positive, then the one that is leaving is negative, must be negative. If you consider the one that enters the node as negative, the one that exits the node must be positive. So as long as you keep this consistent for however many current that enter or exit a single node, everything is fine. It's the same as when you have a linear equation, you multiply both sides of the equation by a negative sign, right? So it shouldn't change the equation, multiplying both sides by a negative sign. So let's say if we have A plus B equals C plus D, right? So now if I multiply both sides by negative sign, so negative A, negative B equals negative C, negative D. So these two are completely equal because both sides are multiplied by a negative sign. So the same is true here too. It is important to have this distinction between the current that enters a node and the current that leaves a node. But as long as you keep that consistent, there is not going to be any issue. So based on this, we can come up with the individual equations. So let's just go over them one by one. So for this, I assume that any current that is leaving the node is considered with a positive sign, and any current that enters the node is considered with a negative sign. So let's just go node by node. So I start with node A. So for node A, and let me just erase this. So for node A, what do we have? For node A, we have IS that is leaving node A. You see, it's in this direction. So we said that anytime we have a current that is leaving a node, I consider it with a positive sign. So we have IS that is leaving the node. And also I have I1 which enters the node through this resistor. So this one I consider it with a negative sign. So IS minus I1 equals 0. So that is the Kirchhoff's law, Kirchhoff's current law at node A. Let's just do the same for node B. For node B, as you can see here, we have both I1 and IC leaving the node. So that means that I consider both of them with the positive sign. So I have I1 plus IC equals 0. So we still haven't found the values for I1 and IC. So this thing still can be true. So if let's say I1 is 5 and IC is negative 5, this summation equals 0. So these negative and positive sign are for the equations themselves, not necessarily representing the sign of the variables, or the value of the variables. So let's just do the same for node C. So for node C, we have IC entering the node, and also we have IL entering the node. So I use a negative side for both of them. I have negative IC, negative IL equals 0. And finally, for node D, I have IL leaving the node, so I use it with a positive sign. And I have IS entering the node, so I use it with a negative sign. So as you can see here, since I used a consistent convention, these currents are usually leaving a node and entering another one. So you see I1 is leaving node A, it's represented with negative sign, but it is entering node B, it is represented with the positive sign. You can do the same for IC as well, or IL or IS, for all of them basically. So this gives us 4 additional equations. So I rewrote them here. So for node A, we have IS minus I1 equals 0. For node B, we have I1 plus IC equals 0. For node C, we have negative IC, negative IL equals 0. And finally, for node D, we have IL minus IS equals 0. So as I said, we had 3 equations from the Ohm's law, and we have now 4 additional equations from the Kirchhoff's current law. So in total, we required 7 equations. But are all these 7 equations independent? That is the important part, right? So having 7 equations is not enough. Having 7 independent equations is enough. The answer to that is not all these 4 equations are independent, because any one of them can be created by a summation of the other 3. So let's say for the last node, let me just add the first equation, the second equation, and the third equation. I just simply add this to see what we get as the final result. So we have IS minus I1 plus I1 plus IC minus IC minus IL. So what do I get after simplifying this equation? We have negative I1, we have positive I1. So these two cancel each other out. We have positive IC, we have negative IC. So if I do this, I am left with IS minus IL equals 0, which if you look closely, this is exactly the same as the last one, except for a minus sign, right? If I multiply this by a minus sign, I get exactly the same equation. So because of that, not all of these 4 equations are considered independent. So that's why we can only use 3 of them. So any 3 that you want. So for the purpose of this example, I use the first 3. So in any circuit with n nodes, this is the general rule. In any circuit with n nodes, you can derive n minus 1 independent current equations using the Kirchhoff's current law. So if you have a circuit that has 10 nodes, out of those 10 nodes, you can only derive 9 independent equations. So you may write 10 equations, right? But only 9 of them are independent. So you need to leave at least 1 out. It doesn't matter which one, you need to leave 1 out. So I repeat it again, in any circuit with n nodes, n minus 1 independent current equations can be derived from Kirchhoff's current law. So this is something that you should always keep in mind. So here we disregard the last one. And as I said, it doesn't matter which one you don't consider, right? you can leave the first one out. It still produces the same result. So now we had three equations from the Ohm's law. We have three additional equations from the Kirchhoff's current law, but we still need one last equation because we were looking for 7 independent equations. So we have 6 of it. What should we do about the last one? To find the last one, it is good, so I define the concept of a closed path or a loop in a circuit. A closed path is basically a loop that is created by connecting elements starting from one end. You can say, for example, here, if you go around the loop without any break in the circuit, you end up at the same node. So if you start from a node in your circuit and you create or you go through the elements of your circuit and you end up at the same location without having any breaks in your circuit, that is what is called the closed path. So here, for example, you can start from node A, go to node D, go to node C, go to node B, and finally go back to node A. So that is what is called a closed path. You can do the same for B as well, B, A, D, C, B. But this is practically the same loop. Even if you go it backward, it is still practically the same loop, right? Because the whole point is that you start from a node, you go in a circle or a loop without any break, and you end up at the same node, right? So going from A to D and C and B and then A is the same as going from C to D and A to B and again C. So now that we have defined the concept of the closed path, it's a good time to see what is the Kirchhoff's voltage law. We saw the Kirchhoff's current law. What is the Kirchhoff's voltage law? So the Kirchhoff's voltage law states that the algebraic sum of all the voltages around any closed path. So you see, this is important. Around any closed path in a circuit equals 0. For the Kirchhoff's current law, it was at any node, right? So no matter what is the node, where is the node in the circuit, no matter how many lines are connected at that specific node, any node has the sum, the algebraic sum of all the currents to be equal 0. The same is true for the Kirchhoff's voltage law. For the Kirchhoff's voltage law, any closed path in your circuit, whether it is small, large, has some smaller closed path inside of it, it doesn't matter. Any closed path in your circuit, if you find the algebraic sum of all the voltages around that closed path equals 0. So here we have one closed path. I can show it like this, or I can show it in the other way too. It doesn't make any difference. So to use this law, an algebraic sign or reference direction must be assigned to each voltage in the loop. As we trace a closed path, or we go around a closed path, if a voltage drop is assigned a positive sign, a voltage rise must be assigned a negative sign, and vice versa. So let's just say I am going through this closed path in this direction, and let's just say I start from node A. I want to clarify what I mean for considering it with positive sign or negative sign. So this is an easy way to do it. So let's just say we start from node A, we want to go clockwise and then come back again at node A. So anytime that you hit a negative sign first, you consider that voltage with a negative sign. So let's just say I go from here to the first element, which is an independent voltage source. So I consider it as negative Vs, because I hit the negative side first, then the positive side. I go around, I get to this one. I hit the positive side first, right? So I consider this with a positive sign, VL. I move past RL, get to RC, I hit the negative sign. So I consider this with a negative sign, VC. And finally, I get to R1 and I hit the positive sign first. So I consider it as positive. So V1 equals 0 because we ended up back at the initial node. So this is the equation that we have based on the Kirchhoff's voltage law. So what if you want to do it the complete opposite? So anytime you hit the negative sign, you use a positive sign to represent that value. So let's just do that and see what we get. So I start again at node A. I get to this independent voltage source. I hit the positive side of it. Sorry, I hit the negative side. I said I use the positive sign whenever I hit the negative side. So I write it as Vs. I get here. Now I need to write it as VL. I hit here. I need to write it as positive VC. And finally get to R1 and I write it as negative V1, so 0. So if you look closely, these two equations are completely the same. The only difference is that from one to another, you have multiplied both sides with a negative sign, right? So as long as you are consistent, it doesn't matter whether you choose to use a positive sign when you hit the negative side of the element or you choose the other way around, right? So it is best if you are consistent. But this is the more preferred way. So I suggest you use this one. So now that we have this, this is the equation that we can come up with, going through the closed path element by element and finding the algebraic sum of all the voltages across the elements in the closed path. So we have VL minus VC plus V1 minus Vs equals 0. So this is the final equation that we want to have. So let's just summarize all of these equations. So the first one, we have V1 equals I1 R1. So that is based on the Ohm's law for resistor 1. So this one is based on Ohm's law. The second one and the third one also are based on the Ohm's law. What about the next three? We found those based on the Kirchhoff's current law. So this is short for Kirchhoff's current law. Finally, for the last one, we use the KVL or Kirchhoff's voltage law to come up with the last equation. So to solve this very simple circuit that contains one independent voltage source and 3 resistors, we need to have 7 independent equations for it to be completely solved. But you might look at the circuit and think that is too much for a very simple circuit, right? What if we have more than 3 resistors in our circuit? What if we have more than 4 nodes? What if we have more than one closed path, right? So when you add those up, the number of equations becomes very large, right? Even for a circuit that, let's say, have 5 different elements, right? And then it is going to be very hard to understand what's happening. So we can make it simpler, at least for this circuit. And the way to do it is to kind of eliminate some of these equations. So how? So for any of these resistors, we know the relationship between their voltage and their current through the Ohm's law, right? So that means that if you know the current in a resistor, you know the voltage across the resistor too from the Ohm's law, just by doing a simple multiplication. So based on that, you can say I only need to have one unknown per element, per resistor, right? Because you already know what is the relationship between the current of, let's say, that resistor and its voltage. So if you know its current, and since you know the value for the resistor, you can easily find the value for the voltage. Or other way around too. If you know the value for the resistor and you find the value for the voltage, just by doing voltage divided by resistor using Ohm's law, you can find the value for the current of that element. So only one unknown, either the current or voltage, is enough for each resistor. So equations 1 through 3 can be eliminated. So now let's see what happens next. So according to Kirchhoff's current law, when only 2 elements are connected to a node, or they are in series, what is called in series, if you know one of the currents, basically one of the elements' currents, you basically know the other one too. So what do I mean by that? So let's just take a look at this force equation. We have Is minus I1 equals 0. So it means that Is equals I1. Let's just see what we get for the second one. We have I1 plus IC equals 0. So that means that I1 equals negative IC. What about for the last one? Negative IC equals, negative IC, negative I1, IL equals 0. So that means that negative IC equals IL. So what do we get using these 3 equations? If we combine all of these 3 equations, we can easily see that that means Is equals I1 equals negative IC equals IL. So all of these 3 equations are basically giving us this result. That if you only consider one, let's say, variable, one unknown, we can easily find out the value for the other one. So if we, let's say, write everything in terms of Is, after we found the value for Is, we know I1 equals Is, we know IC equals negative Is, and we know IL equals Is again. So that's another way that we can simplify or reduce the number of equations. So if we do that, we basically write everything in terms of Is. What we have is here for VL, we had VL to be equal IL multiplied by RL. For VC, we knew it was IC multiplied by RC, and for V1, we knew it was equal I1 multiplied by R1. So we basically, what we do is that we use this equation And for any of the currents, we use IS. So here IL multiplied by RL becomes IS multiplied by RL. Why? Because IS and IL are exactly the same. For IC, we know that IC equals negative IS, or IS equals negative IC. We just replace this with negative IS and we write this term. We do the same for V1 as well. So I1 equals IS. So that means that here V1 would be equal to IS multiplied by R1. And then finally we have Vs itself equals 0. So the whole set of equations that we had for that specific circuit is going to be simplified to this very basic equation. If we know value for RL, RC, R1 and Vs, the only thing that we need to find out is the value for Is. When we find the value for Is, we practically have the value for I1, negative IC and IL, and when we know these, we can find the values for VL, VC and V1. So practically we don't need to solve 7 linear equations simultaneously, right? With a little bit of manipulation, we were able to simplify the whole circuit into one single equation. Of course, when we talk about more advanced techniques, you will see what is the reasoning behind these simplifications as well. So what we learned in this video, we learned about the Kirchhoff's current law, which states that the algebraic sum of all the currents connected to a node, all the currents that enter or exit a node equals 0. We also saw Kirchhoff's voltage law, which states that the algebraic sum of all the voltages of the elements that are inside the closed loop equals 0. And we also learned how we can use these two techniques to come up with the equations for solving circuits.